F5, yeah. They're just right outside.
Okay. Okay, you went outside?
Yeah, they're just right outside waiting for you. Oh, it's 2:21. April 22nd. All right. So we're working on a little bit different than the other class. We're working on double slits. We're looking for a little more detailed idea of what's going on. So the idea being that this will be a bright spot. Or actually, this is just a spot. Might be bright, might not be bright. That's L1, and that's L2. And depending on the length of the path, those two sine waves add in phase or maybe not. It's rather obvious that one is longer than the other, right? So what we're thinking is, or what we're trying to illustrate, is that, well, maybe one of them is doing this. We'll call this the short one. There's our screen. See if I can do it. The other one travels a little farther. And it's doing that. And hence, these two waves are not in phase. And our phase difference, I'm going to call our phase difference delta phi. It's 2 pi delta x over lambda. And this is our delta x. Now, what we're trying to do is, at this point, we're trying to add our two electric field vectors, E1 and E2, to get E net. Now, what do you know about electric field vectors? I'm looking for one particular fact. Electric field vectors as part of light and electromagnetic radiation. The electric field vector is transverse to the direction of motion, right? So this is our electric field vector. Our electric field vectors are either up or down, which, when I look at this page, I really mean either in or out of the board, because it's top, you know. Actually, it doesn't make any difference. Yeah, it does. Our electric field vectors are coming into or going out of the board. So I can draw it like so. Electric field vectors. And now I want to account for this little bit extra distance here, this delta x. And delta x is equal to d sine theta, where this distance is d, and this angle is theta. Hello. So, we're going to write our electric field vectors, and the nice thing is they're pointing up and down, or either into or out of the page. So they're really only in one direction, and I don't care about the vectors at that point. And E1 is E naught sine of omega t, omega being related to the angular frequency. And E2 is E naught sine of omega t plus delta phi. That's because it travels a little bit farther. There's a little bit of an additional angle involved here. And so what we're trying to do is add these two waves together. So, E net is equal to E1 plus E2, which is E naught sine omega t plus E naught sine omega t plus delta phi. Now, what would you do with that? Can we simplify it? Yes? How? Can't do that. But you can pull out the E naught, but you're still left with the sine omega t plus sine omega t plus delta phi. You have to remember those trig functions are functions actually, and you can't, they're not just they're not just parentheses, they're actually functions. So back in the day when you took a trig course, right? Some point in time? Yeah? Really long time ago. But you ran into something that looks like one of your unused favorite trig identities. The sine of A plus the sine of B is equal to 2 times the sine of A plus B over 2 times the cosine of A minus B over 2. Okay, use that trig identity and do the math. So I end up with 2 times the sine of omega t plus delta phi over 2 times the cosine of negative delta phi over 2. But knowing that the cosine is an even function, that is, the cosine of a negative angle is the same as the cosine of a positive angle, we can write this as 2 times the sine omega t plus delta phi over 2 times the cosine of delta phi over 2, and just drop that negative sign. Put that back together, and we have E net is equal to 2 E naught So, did we get there? Do you have that on your page? Okay, now, intensity of light. Is proportional to E squared. We'll need a constant, so we'll say this is proportional to A times 2 squared E naught squared sine squared omega t plus delta phi over 2 cosine squared delta phi over 2. All right. So what you got is intensity is a function of time and phase. Pardon? Oh yeah, just to remind yourself that you did that whole thing, that you actually squared that whole thing. Often it's good to leave yourself little signposts of where these numbers came from, because as you're going to see, a lot of things are going to happen. Now, if I wanted to think about measuring that, it's a function of time, which is bad news, because that means it changes in time, right? There's this t here. But, and what we did last time, and this is why we did it last time, if we take the average of this thing, what will happen? Now we want I average. Well, A doesn't change. The 2 squared is still 2 squared. E naught squared is still E naught squared. What happens to the sine squared thing? It becomes 1/2. What happens to the cosine squared thing? It's not 1/2, because it's not a function of time. We're integrating it over a period, so that's just a number. But thank you for volunteering. So the average over one cycle, remember, is how we got rid of that. So there's our ugly function. inspiring is that ugly function? Not very. So let's make it a little bit more inspiring. There's our same two slits. And now I'm interested in one point on the screen in particular, this one right there. It's the middle point right behind it. And it's a rather special point. It's a bright spot. What do we know about this bright spot? It's a bright spot, yes. It's located in the center, right behind the slits. Right behind the, well, the center of the slits, right? It's right there. For that spot in particular, what's the phase difference between the two beams? 0. Do you have a reason, or you just happen to like 0? You like 0. I don't blame you. The distance is the same, so the phase difference is the same. And so let's use our formula, but for a particular spot, this particular spot, we'll call it I naught. I naught average equal to A times 2 squared E naught squared times the same 1/2 cosine squared 0. But cosine of 0 is 1. So this makes I naught equal A 2 squared E naught squared times 1/2. All right. Now, at last, we can do this. We can talk about I over I naught, which is A times 2 squared E naught squared times 1/2 times the cosine of delta phi over 2 squared divided by A 2 squared E naught squared 1/2. And what do you see happen? All that junk goes away. All of that goes off with all of that. So now we can talk about the intensity is equal to I naught times the cosine squared delta phi over 2. That's intensity as a function of phase difference. So what's the condition in terms of phase for constructive interference? Or talk to me about constructive interference. Constructive interference, what's the condition that two waves interfere constructively? When the waves meet. But they might not be in phase when they meet. So if I went back, if these two waves were adding to the same point on the screen, would they interfere constructively, destructively, or something in between? Something in between, right? The top one is all the way at its highest peak, and the bottom one is coming down again. So, what condition? Well, there you go. There's our. Well, that's our relationship between phase and path length difference. What condition, maybe in terms of path length, if delta x would produce constructive interference? 0? Any others? One lambda? If I shift it over by a wavelength? Or 2 wavelengths? Or 3 wavelengths? Or m wavelengths? Delta x is equal to m lambda. So what that means is I need to express my intensity in terms of lambda, right? Let's do it this way. I is equal to I naught cosine squared. Instead of that delta phi, I'm going to put in that other expression, 2 pi delta x over lambda. And of course I still have the 2 in the denominator. The 2 in the denominator goes away with the numerator. I naught cosine squared pi delta x over lambda. Now, when delta x is equal to m lambda, well, what do you know about the cosine squared of an integer times pi? One. What does that tell you about constructive interference? Can we say anything? How do we interpret that? It's constant. So all the bright spots have the same intensity. What about destructive interference? delta x is 2m plus 1 times lambda over 2, where m could be 0 or 1 or 2 or 3. Let's go ahead and put that in there, and then we have I is equal to I naught cosine squared pi delta x over lambda, so pi times 2m plus 1 divided by lambda. Odd multiples of 1/2, like 1/2, 3/2, 5/2 pi. What's the intensity? Take the first one, cosine squared of 1/2 pi. Pi over 2, 90 degrees. 0. So in fact, they're all going to be 0. All half multiples of pi are 0. Destructive interference, the intensity is 0. No light gets there. Finally, delta x delta phi rather is equal to 2 pi delta x over lambda, but we're going to rewrite this as 2 pi d sine theta over lambda. This is our double slit condition. So now we have intensity as a function of angle. Now we need to do a little bit of trig here. Find the angle where the intensity is 1/2, i.e. something in between, not 1, not 0, but 1/2. Half is bright. Solve that for theta. Tell me what that theta is in terms of lambda and d. Do a little bit of algebra on that and see if you can't come up with an expression. That's more inverse trig functions than you ever want to see in one equation. What's the problem with inverse trig functions? Restricted domain. They're not nice functions. That they're not defined over the 0 to 2 pi range. So they're multiple valued functions, both of those. All right. Let's make D 0.25 millimeters and lambda to be 670 nanometers. We got a bright spot, and 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 a bright spot. Where do you think we would look for this place for the intensity to be 1/2 of the maximum? So what do those yellow dots represent on the picture? Bright spots. What's halfway between the bright spots? Dark spots. I should color those in. There's my dark spot. Now, what's halfway between the bright spot and the dark spot? Or between a bright spot and a dark spot, maybe not necessarily halfway, but some place where the intensity is not maximum, but not minimum. So wouldn't you expect the first one to be right about here someplace? And the next, whoops, where'd you go? Come back here. First one there, next 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 one there, and so on. Hence your multi-valued function. Well, you got your calculators. We got D, we got lambda. Come up with the first two angles. Be careful as to the mode of your calculator. In fact, yeah, and this is a little caution. This argument in this one is implying that we're in radians because of the pi. So you can work the first one in whatever units you like, but the argument of the second one is definitely radians. Well, actually, wait a minute. The sine inverse. Cosine inverse of pi over root 2 is pi over 4. Yeah, you can do that. So theta is going to equal sine inverse. Right. Actually, this is a number, so you're okay as far as Well, you have to be right careful because you wouldn't want to write that as 45 degrees. That's where you would be mixing things up. And pi d pi over 4. I get 0.0383 degrees as the first angle. What's another angle that has the same sign? Multiples? Really? Yeah. So on the unit circle, this is supposed to be a unit circle. Not very circular, but you get the idea. These two angles have the same sign. How are they related? That one and that one. So if theta 1 is 0.0383, what's theta 2? 180 minus 0.0383. So that's one place where we've got a multiple angle issue going on. The other place that we've got a multiple angle issue going on was right here with that pi over 4. Cosine inverse of pi over 4. How did we mess that up? Cosine inverse of root 2. What other angles have that same cosine value? Pi over 4. And let's keep going in the positive direction. What's the next one? 3 pi over 4 has a negative cosine. Remember, on your unit circle, the cosine values are on the horizontal and the sine values are on the vertical. So if this was pi over 4, the other one is down here. Which is, what angle is that? 2 pi minus pi over 4. Which is 8 pi over 4. Pi over 4 minus pi over 4. 7 pi over 4. So we can get another one of these angles. Instead of putting that in, we can put in that, and you can generate more of these angles. So partly this is an exercise in being really careful with your sines and cosines, always a very important point. But we can get the intensity at any point on the screen. Let's see if we can do that one. Theta is equal to the sine inverse lambda over d 7 over 4. So this is probably our theta 2, which is equal to 0.2687. All right, moral of the story, you have to be able to deal with inverse sines and cosines, and just be careful. The unit circle is your really good friend on that kind of stuff. All right, we're going to stop there. Next Monday, we need to talk about black body radiation. It will be our last topic. We have 3 Mondays left, so we'll spend the next 2 Mondays black body radiation, and then we'll take the final on the last one. And remember, the final, you can do perfect on it to get an A in the class. It'll be very similar to what you did in the midterm, but you won't make those mistakes, and you'll be warned ahead of time of what subject we're looking at. We okay? Cool. But if you have a chance between now and next Monday, look up what black body radiation is. We're done. Thank you.